Welcome to the next session on virtual labs. In this session, we are going to discuss about the fifth experiment of Machine Dynamics and Mechanical Vibrations Lab. The title of the experiment is Base Excitation. This is a continuation of experiment number 4, wherein we have discussed about the forced vibration of single degree of freedom system. There we discussed that there are three cases, or rather we would say that there are three ways of excitation to the system forcibly. The first case we have already discussed in experiment number 4, that was by applying harmonic force. Here we are going to discuss about base excitation. Let's start with the experiment. The aim of the experiment is to observe the effect of damping in forced vibration of single degree of freedom due to base excitation. Let's see the theory part of this experiment. When an applied force causes the system to vibrate, it is considered as a case of forced vibration. An external excitation is often reduced to one of the following types. The first one is external harmonic force, which we have discussed in experiment number 4. This is the equation. Base excitation has this particular equation, mx double dot plus cx dot plus kx is equal to f, where this f is nothing but cy dot plus ky. C is the damping coefficient, y dot is the velocity, k is the stiffness of the system, and y is going to be the displacement, which is given by this equation. Y is equal to y naught sine omega t. This is the motion of the base. This equation is going to govern it. Y naught is the magnitude of the displacement. The displacement is of sine form, and omega t is the phase over here. T is the time and omega is the angular velocity. Next is rotating imbalance. This is the next experiment in line. So we will discuss in the next experiment itself. I have already given an explanation for this in the experiment number 4 in case you wish to go through it. We will see the solution of the system. The solution of the forced vibration system consists of a steady part and a transient part. We have already discussed this in the 4th experiment. The steady state response is independent of the initial conditions. The transient part comes to 0 with time and is usually neglected. The steady state response is of the form amplitude in terms of time is equal to x naught sine of omega t plus phi. X naught is the amplitude, phi is the phase of the steady state vibration. For y is y naught sine omega t, base excitation, the steady state amplitude is going to be given by this formula. X upon y is equal to root of 1 plus 2 zeta eta the whole square upon root of 1 minus eta square the whole square plus 2 zeta eta the whole square. Here zeta stands for damping factor and eta stands for frequency ratio. Eta is omega upon omega n. It is the ratio of operating frequency to the natural frequency of the system. So here we are going to use this equation of x for calculating the amplitude. This capital Y is nothing but this y naught that you see here. So whatever magnitude of force you have given, you're just supposed to substitute here. And x is what we are going to calculate. X is the amplitude of forced vibration. Also you can note that x upon y is called as motion transmissibility. Now next we'll discuss about the procedure. Like in the 4th experiment, the same procedure has to be followed here. This is the window of base excitation. Here we are going to change the value of stiffness, mass and damping ratio. We are going to vary these three values. We can also change the excitation magnitude and excitation frequency. Then we will start the experiment. We will get some value of omega n, eta and zeta. Zeta is something that we are setting. Eta can be calculated from the value of omega and omega n. Omega n is here and omega is what you're giving here. So it's the ratio of both of them. So when you click on the graph, you're going to see a graph of transmissibility versus the frequency ratio. Also, you will get a graph of phase angle versus the frequency ratio. This is for the first value of zeta. Say the zeta is going to be very small. It is less than half of 0.707. Next, we are going to give a different value of zeta, which will be between 0.35 and 0.707, and we will obtain another graph. We will keep the value of stiffness, mass, excitation magnitude, and excitation frequency same. We are not going to change those values. Then we will see a graph like this for the second value, and then again we will change the value of zeta, which will be greater than 0.707 now, and we will find out the graph for it. So that's all we are going to do here. This is similar to the fourth experiment. I'm repeating again and again because it's the same explanation that I've already given there. This is the self-evaluation tab. You can go through this and solve the entire one and find out the answers. The formulas are already given in the theory portion. So we will go to the simulation tab. Here you can see the stiffness is what I'm going to set. Also, I'll change the mass to say 48 kg. The damping ratio initially has to be less than 0.35 as we know. So let me set it to 0.15. The excitation magnitude is 20, that's okay. And excitation frequency is 50 radians per second. If you want, you can change this. So you can see based on the value of K and M, omega n is already calculated. It is 51.8656 radians per second. Eta and zeta is also here. Zeta is what we have given and eta is calculated from omega upon omega n. So let's take the graph. Here you're getting the graph of phase angle and this is the graph of transmissibility versus frequency ratio. So we'll just click on these arrows and we are coming back to the experiment. Now we will change the damping ratio to more than 0.35 and less than 0.707. So let me set it to 0.45. So this is how it is going to now oscillate. You can see the damping has increased and so the output has also reduced. The displacement has reduced with respect to time. Here you can see eta is calculated and zeta value we have just provided. So we will see the graph for the second reading. This is the phase angle versus frequency ratio graph. And this is the transmissibility versus the frequency ratio graph. Okay, the last reading we will take for damping ratio more than 0.707. You can see here zeta is 0.86, eta is calculated and omega n is still the same because we have not changed the stiffness and the mass value. We'll go to the graph. This is the first graph obtained and this is the second graph of transmissibility versus frequency ratio. Okay, so this is the simulation tab. Next, we will go to the assignment tab. You can see here, you can just try this question. Next is the quiz tab. Here you can solve these questions and figure out the answers. You just have to click on it and submit the answer. If it is wrong, it will give you a wrong mark. Otherwise, you will get the right answer. Then the simulation demo has been provided for explanation of how to conduct the experiment. These are the various references for this experiment. And finally, there is a tab for feedback. Once you're done with the experiment, you can provide a feedback on your experience of learning through virtual lab. So with this, I end the session. I hope you have understood how to analyze a forced vibration for a single degree of freedom system, which is subjected to base excitation by using virtual labs. If you have any doubt, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.